we're going to try to finish out this chapter 5 today and take us into chapter 6, which will require us to know chapter 5 and also know some of the math that we've done heretofore. So stay with me. I'm going to backtrack a couple slides here. Make sure that you remember what we talked about last, how to name things. There were several slides that had a big procedure on it, but when you actually get into doing it, kind of easier just to use some examples to get through it. So in this particular case, how would you, and this is one that we've already went over, but the question was, how would you name this compound? The first thing that we need to do is to see if it's something that would be called something by a common name. And this is not. It's not ammonia, it's not water, it's not salt or sugar or anything like that. Technically, it's a type of salt. Any ionic compound that dissolves in water is technically called a salt, but not table salt. So the next question is to decide whether it is ionic or molecular. Which one is it? It's the only one we've talked about so far. Ionic. The next question then, if we know it's ionic, we've got to decide, is it a type 1 ionic or a type 2 ionic? What do I look for? What do I focus on to answer that question? The type of metal. Okay? If it's type 1, the metal will have only one charge ever associated with it. If it's type 2, it will have multiple charges, and it's going to be in that transition element block because we can't predict its charge very well. So what is iron? Is iron a transition metal? Yes, it is. So what this tells you is that whenever you name this, it's going to be iron something in parentheses to indicate the charge. Okay? Now, this NO3, what is that? That is a polyatomic ion called nitrate. You have to know your polyatomic ions. Nitrate has what charge? A negative 1. Nitrate has a negative 1 charge. Okay? Now, this particular scenario suggests that you have an iron atom here, an iron ion, more specifically, that has some charge that we don't know that we have to indicate in the name. We do know this, and this is nitrate. And when we name anything with polyatomic ions, we just use the name of the polyatomic ion. That's how we name it. Okay? We don't have to drop 8 and add "ide" or anything like that when you have the polyatomic ions. We also can deduce the charge of the iron in this case. How do I know the charge of the iron? Okay, it's the opposite of what I would have in terms of the negatives, right? However, how many total negatives do I see in this particular compound? 3, because each nitrate brings with it a 1 negative charge. So I've got 3 of them. So what does my charge of iron have to be? Positive 3. So this would be named what? Good. Iron 3 nitrate. So here's all the steps that we just went through. Blah, blah, blah. There we go. Do-do-do. What thing? No, I think I just positioned it differently. It must have been pointed a different way or something. But now you jinxed me. See? Oh. All right. Now, let's look at a different one now. We've talked about ionic compounds. Let's look at molecular compounds. These are going to be made from nonmetals. 2 nonmetals stuck together. That's how you can recognize this. You won't see any metals in this particular formula. How do you name molecular compounds? Well, one of the other things I had you memorize on that sheet of polyatomic ions was prefixes, and this is why. Okay, you're going to use prefixes for these types of for naming a molecular type of compounds. So you're going to say, basically, look at the boxes down here. You're going to have, we're going to stick with 2 things together. Now, obviously, chemistry doesn't always exist like that. There are sometimes many different elements that can be stuck together, but we're going to skip that. For this class, we're going to just look at what if we have 2 of them together. All right, we're going to name the first element. You just give me the name of it. So as long as you studied the elements on the periodic table, we've already taken that quiz, you should know the names of most of these elements. So you just name it. And then you put a prefix in front of it that tells me how many of them are there. Unless it's mono, in which case you leave that off. Okay? Over here, you're going to take the base name of the second element. So say the second element was sulfur. You'll take the sulfur, drop the ending, and add "ide," like we did with ionic compounds. So it would be sulfide instead of sulfur. Okay? And in front of that, you would stick a prefix telling me how much was there. Now, you will only use prefixes with molecular compounds. You will not use prefixes in ionic compounds. Understand that, because people try to do that. If you see FeNO3 in parentheses 3, like we saw a minute ago, that's iron 3 nitrate. That's not iron trinitrate. If you were in chemistry, that would sound foolish. Okay? It's iron 3 nitrate. Molecular compounds only, when no metals are present and only nonmetals are there, that's the only time you're going to use prefixes. So make a note. Okay. Like I said, we're not going to go over the rules for things of more than 2 stuck together. Never use the prefix mono on the first element. For example, CO2, you know, is named what? How do you say that? Carbon dioxide. You don't say monocarbon dioxide. Okay, it just sounds kind of dumb. So if the very first prefix is mono, leave it alone. Don't mess with it. We've already talked about all these. You should know them. Mono, di, tri, tetra, penta, hexa, hepta. See? Look what you've done to me. I was doing fine. So you tried to cast some hex on me. You really done it too. Yeah, but... Okay. Well, anyway, those are the prefixes you were supposed to know. You already know them anyway. So let's look at this binary molecular molecule. Binary means 2. There's 2 atoms here that make up this molecule. It's a molecular compound. There's no metals present. You see 2 elements present. What are those 2 elements, first of all? Just give me the element names. Boron and fluorine. Okay, good. Now, how do I name this? Well, since there's no metals present, we'll use a different naming mechanism, the one I just showed you. Is it one of the common exceptions? No, so we don't have to worry about that. What class is it? Is it ionic or molecular? It is molecular. There is no metal present. Okay. All right. Name the first element, we said. It was boron, right? Name the second element with an "ide." So fluoride, not fluorine. Add a prefix to each name to indicate the subscript. So monoboron, trifluoride. Then what do we do with that mono? We drop it. So the name of this is boron trifluoride. Easy enough. These are the easiest ones to name. You've got to know your prefixes and you're in good shape. All right. This is ridiculous. All right. Moving on to acids. Let me see if I can make a difference here, if this will work or not. I don't know. I think I tried this the other day and it didn't work, didn't I? We'll see. Maybe it will. Okay, acids. Acids are a little bit different. Now, acids technically would fall under molecular type of compounds, right? Because it's nonmetals that are involved. But it's such a special situation that I want you to recognize it as something separate. I want you to recognize if you have nonmetals together, where you would normally have a molecular compound that you are naming using your prefixes. If you see hydrogen as your cation, as it's present, it looks like there's no metals. This is what's different about it. There's no metals present, but yet there are ions present. There's positive and negative charges because the positive charge is going to come from the hydrogen. This is odd. This is why hydrogen's over on the left side. It forms a positive charge, and it's the only non-metal that really does that. Okay? Everything else is usually metals that form positive charges. So if you see a positive and a negative charge, and the positive comes from a hydrogen that's present there, then you have what's called an acid. Because what will happen, and I'll talk about this the very last chapter that we discuss in the semester, but what an acid can do, and what it will do, by definition, is release its hydrogen to react with something else. That's why they're so dangerous. Okay? When they put them in solution, they dissolve, and that hydrogen falls off, and it floats around, and it can react with other things. So acids are going to contain hydrogen ions, a hydrogen cation, plus some sort of anion that will be present, some negatively charged thing. That's going to take place in an aqueous solution. Now, that just means that it's going to be dissolved in water, for example. Now, binary acids, binary means two. So acids that are just have two things present, hydrogen plus one other element stuck together. They're going to have a hydrogen cation and a non-metal anion. You could also have, like, for example, HCl, HBr. Those would be binary acids. Okay, only two things involved. Now, oxyacids are going to involve your polyatomic ions. It's going to be hydrogen as your cation and one of your polyatomic ions as your anion. Okay, like NO3. Nitrate and a hydrogen ion together make what's called nitric acid. Okay, I'll teach you how to name that in a second. But that will be an oxyacid. You can recognize that. It's not binary because there's more than two things present. In all your polyatomic ions, there's more than two elements there. There's oxygen and like one or two other things always there. So when you put them all together, it's more than binary. Okay? So oxyacids still have the hydrogen as a cation, but it'll involve a polyatomic ion for its negative side. So we've split this up. Acids can be binary or oxyacids. Your giveaway, look and see. Is this thing, what I'm looking at here, if it's not some sort of an exception, is it ionic or molecular? Well, it appears to be ionic because it has positives and negatives. It appears to be molecular because it has no metals present. Okay, so that's sort of a unique situation, and you can identify the acids as such. Okay, so how do you name, given the formula of an acid, how do you name that acid? That must not have been it. I must be shorting out on this thing or something. All right. Like I said, they sort of look like they're made of ions. They tend to have the word acid at the end to clarify what we're doing here. Oh, this is good. If you have a binary acid, what you will see, so like HCl, HBr, those kind of things, what you will see is that there's a prefix of the word hydro in front of the name that you're going to make. Okay, so it'll be like, for example, HCl is hydrochloric acid. Okay? Now, and you're going to take the base stem of the nonmetal and make it ic. So, for example, if I have hydrogen and chlorine, and I'm making a compound that is an acid out of those things, I'm going to put them together. I'm going to put the word hydro in front of it because the hydrogen's there. That's where it comes from. There's two things, so I call it hydro something. I take the name of this anion, chlorine, I drop the ending, and now I add ic. Okay, so hydrochloric acid. What would be HBr? Hydrobromic acid. Don't forget the acid on the end. What would be, see if you can get tongue-tied on this one. What would be HI? Hydroiodic. That's how it's done. Hydroiodic acid. But yeah, you're right. I was just trying to confuse you. Okay. Okay, now if you have an oxyacid, so you got some polyatomic ions involved with what you're dealing with here. Now, this gets a little more detail here. If the polyatomic ion ends in ate, like nitrate, okay, you're going to take the name of you're going to name the acid by taking the name of your polyatomic ion and changing ate to ic. Okay, now let's look at an example. HNO3. I used this one a second ago. HNO3. The fact that you have H at the front gives it away that it's probably going to be an acid. Okay, so HNO3. It's not a binary acid, so it's not hydro something ic acid because there's more than it's an oxyacid. All right, hydro is out the window. We don't even use the word hydro now. Whenever you're dealing with oxyacids, you're going to name the acid according to the polyatomic ion that makes it up. Okay, so if it's ate, like in nitrate, you change the ate to ic. So nitric acid. That's HNO3. HNO2 is made from a hydrogen and a nitrite ion, right? So hydrogen and nitrite, if it ends in ite, you change it to us. This is going to be a little confusing, so you just have to just remember this. Ate to ic, ite to us. There's probably some fancy way you could remember that. Okay? So HNO2 would be called what? Nitrous acid. Nitric acid, nitrous acid. Difference. Okay? Sulfuric acid, sulfurous acid. Okay? One comes from sulfate, one comes from sulfite. It depends. You have to look and see what polyatomic ion is attached. All right. Here we go. Here's an easy one. You know this just from basic science classes that you've taken before. But why is it named what it is? Let's look. Is it one of the common exceptions? Well, you may be able to argue that. If you ever go to Lowe's and buy muriatic acid, like in the place where you buy the concrete or paint thinners and that kind of stuff, you can get muriatic acid. That's actually hydrochloric acid. But we'll say no, it's not a common exception. All right. Identify its class. The first element listed is a hydrogen, so therefore it's going to be an acid. Okay? Identify the subclass. Is it binary or is it oxyacid? It's binary. There's only two things there. So what do you know is going to be at the beginning of this name? Hydro. What is going to be at the very end of the name? Well, okay. You're right. You're both right. The very, very end is going to be the word acid. And then at the end of the anion, you're going to have the word "ic," the suffix "ic." You're right. Okay, so identify the anion involved. It's chlorine, right? So it's an anion form. It's called chloride. Well, we change that to "ic." Drop the "ide" and make it "ic." So chloric. So you're right. You put the hydro in front of it, hydrochloric, and then you write the word acid at the end to add a little spice to it, make it sound a little better. Hydrochloric acid. What about this one? We got to break it down. Now we know it's not a common exception. It's an acid. Okay, it's got the hydrogens in front. Now there's two, but there's still hydrogen atoms in the front, ions in the front. So we have to count this as an acid. Is it binary or oxyacid? Well, it's an oxyacid because what is the name of that? The polyatomic ion, sulfate, right? It's not sulfite, sulfate. Why is there two hydrogens with it? What's the charge of a sulfate? -2. So you got to know your polyatomic ions and their charges, right? This is a -2, so there has to be two hydrogens there to balance that out to get this formula, H2SO4. How do we name this? So we name it according to the polyatomic ion present. We don't need to have the word hydro in front of it. Okay? This is sulfate. You told me that already. So if it's an 8, we change it to "ic." If it was an "ite," we would have changed it to "us." So we say sulfuric. You take instead of sulfic, you might want to think like sulfic or whatever. What actually is all these things involve oxygen. So it's sort of like you just kind of ignore the oxygen in it. The base here is sulfur. So when you start doing these names, some of them will sound right, some of them won't sound right. Okay, you'll get the hang of it. It's pretty easy to pick up. But this would be sulfur, so sulfuric. If this was a P, it would be phosphoric or whatever. Okay, it would sort of ignore the oxygen that's present there in the name. All right, so sulfate would become sulfuric. This is called sulfuric acid. Okay. If this was H2SO3, what will be the name of that acid? Sulfurous acid. Sounds meaner, doesn't it? You got fury behind it or something. Oh, I just gave you that. I didn't know that slide was there. Okay, so we said that this is ridiculous. We already went through this. This is sulfite. If it was H2SO3 instead of H2SO4, you said since it was "ite," we're going to change it to "us," so this would be sulfurous acid. Okay? Now, there's your handy-dandy flow chart. This summarizes everything. So if you've had a little bit of trouble up until now, if you've got the hang of it, super. If not, you'll probably want to go online and print out one page of that big so that you can use this to do all the homework problems. Okay? But you can certainly follow through the same reasoning process. Is it something common? If not, start here. Which one of these three is it? And follow the chart. You can separate it all down, and this is how you can name all this stuff. This will not be on the test for you to use. I promise you that. Okay? All right, let's work the other way. So far it's been pretty easy. I've given you the formula, and you had to give me the name from the formula. However, what about if I give you the opposite? What if I give you the name, and you've got to give me the formula? It's everything that we just did except thinking in reverse. Okay? So it shouldn't be that bad as long as you follow what we've done so far. This is easy. I'm going to start with this one. For binary molecular compounds like CO2, it's really super easy to figure out the formula for these things because it tells you the formula in the name. What do you think the formula is for dinitrogen tetraoxide? Dinitrogen tetraoxide. Oh, what? 4. Tetra is 4, right? Think of the Nintendo game. All the shapes had 4 blocks to them. That's why it's called Tetris. Okay? The N2O4, dinitrogen tetraoxide, it's easy if you're dealing with molecular compounds because it tells you in the name how to write this thing. So, now, for your type 1, type 2 ionics and your acids, you've got to realize the steps that we've already employed and just sort of work backward a little bit. Okay? You'll see what I mean. This one's easy. We just did something similar. Dinitrogen pentaoxide. You've got to figure out what elements are present. Dinitrogen means you're dealing with nitrogen, so that's N. Pentoxide means O. That oxide comes from the element oxygen. So you've got N and O. Now you've got to determine what ratio is there. How many N's, how many O's? Well, 2 and 5. So N2O5. That's simple. All right? Now, realize that if you're going to now write the formula for something that involves ions, what you have to do is balance the charge. You have to make sure that in the end, when you give me a formula for a chemical compound, that there is no residual charge left over, because that's why compounds form. The reason chemical compounds form is because ions of different charges come together in an attempt to neutralize themselves. So whatever you have has to be a total of a charge 0. You've got to keep that in mind as you're trying to figure this out. Now, take this one. If the sodium ion is combined with a, how do I say this? Is this sulfur? How would you name this? This ion right here. Sulfide. Sulfide. Don't think too hard. You don't need your prefixes unless we're naming compounds. Okay? We're not going to have any Roman numeral type of situations like sulfur 2, sulfur 4. That's only with metals that are transition metals. Okay? Here, we just say that would be a sodium ion. This would be a sulfide ion. Okay? If this were the case, and you were combining sodiums and sulfides, how many of each would you need? You would need 2 of these for every one of these, right? Because you got to balance this out. There's a 2 negative here. The only way you can get 2 positive is to have 2 sodiums, all right? That's what this is saying right here. So the way that you would write that formula is Na2S. Tells me that these are all hooked together, and there are 2 sodiums hooked onto that and 1 sulfur, okay, 1 sulfide ion to balance out the charges. Okay. So the first thing you want to do is figure out what metal you have if it's an ionic compound. Write the metal cation and its charge, assuming that you know its charge. If sodium, you know its charge. If it's a transition metal, you don't. Okay? But let's say that we do know it. You write the symbol for the non-metal anion and its charge. So you've got symbol and charge. Symbol and charge. Now you've got to figure out how they go together with one another in terms of how many of each. Okay? Now I'm going to show you a cheating shortcut, but make sure you double check everything. I'll show you steps 3 and 4 here in a second with the next example. Look what I mean. Write the formula of a compound made from aluminum ions and oxide ions. Anybody have aluminum siding on their house? All that white powder that forms all the time, that's aluminum oxide. Okay, so you've got an interaction of aluminum ions and oxygen from the environment. Here's what we know. To write a formula for a compound that's involving aluminum ions and oxide ions, we need to know, first of all, what ions are there, how to write them. We know that Al has a 3 positive charge. It's given on our periodic table. I told you to write that down. So Al 3 positive. What's the symbol and charge for the anion? Oxygen. Every oxygen is a 2 negative. So I know this to be true. Now what I've got to figure out is in what proportion must these things come together to create a charge-neutral situation? Now, there's a couple different ways you can go about this. You can realize and start imagining them appearing in your head, like, okay, bloop, bloop, bloop. They start popping up, and you have some oxygen sitting over here, you got some aluminum sitting over here. How many of each would have to come together to balance everything out? Go back to some basic math here. Think about least common multiples. Okay, what's the least common multiple of 2 and 3? 6. Okay, so you can't have 1 aluminum and 1 oxide. That's not balanced. You can't have 2 aluminums and 2 oxides. That's not balanced. What you have to have is, you're going to see that through least common multiple, the first place you can get to that they share in common in terms of how many of them you can bring in is going to be a 6 for its charge. Okay, so what do you need to get a positive 6? How much of this do you need to get a negative 6? 3. So there's going to be 2 of those, 3 of those. They're going to come together and they're going to balance out. Okay? Now that's what you need to understand is happening in your head. Now just to get the formula, so you can then double check it, there's even an easier way than that. You can actually take and switch them. You can take their charges, switch them down to the corners, and they become the subscripts. Okay? So Al3 positive, O2 negative. We said a minute ago you would need Al2O3 as your answer, right? Well, look, bring that there, you've got Al2O3. Now, if you do that, that's fine, but double check. Okay? Make sure that that works in your head. Okay, if I have 2 Als, what's my charge? 6 positive. If I have 3 Os, what's my charge? 6 negative. It all works out. Just double check it if that's the step that you want to use. Now, at that point, what you have to do is take a look at this and reduce it to simplest terms. If this was 4 and this was 6, you would reduce that to 2 and 3. Okay? So make sure at this step you would reduce. In this case, we don't have to. That's the simplest form. Okay, so this is where we're double checking. You've got a 6 positive, I've got 6 negatives, we're balanced out. So to write the symbol for a compound that would form between aluminum and oxide, aluminum ions and oxide ions, you would get Al2O3, 2 aluminums for every 3 oxides present. Okay. Try not to look down, try not to cheat. Let's see if we can do it in our head here. What are the formulas for the compounds made from those ions? If you had potassium and a nitride ion, potassium has what charge? +1. Nitride would have what? -3. So how would you write that? Na K3N. You'd have to have 3 potassiums to balance out that negative charge from the nitride ion, from nitrogen. Calcium with a bromide ion. Let's see if I'll write it up here. Calcium, what's calcium? Ca2 positive. What's bromide? Br negative, right? So what would my formula be? Good. Aluminum. Al3 positive, the aluminum ion. Sulfide ion. S2 negative, or -2, however, doesn't matter. What do I get? Good. Double check. Al2 means there's 2 of them, each with the 3 positives, so there's 6 positives. There's 3 of these, each of them with the 2 negatives, 6 negatives. It all works. Okay? So there we go. You can do it. Yeah, no group test, sorry. All right, now, let's kick it up a notch. We're still all right. Now, don't sigh. It's not that bad. We're fine. Same thing we've been doing. Manganese 4 sulfide. What does this mean? First of all, answer that question. Manganese 4. The presence of that Roman numeral tells you what? There you go. The charge of the manganese. It's easy now. You got it figured out. So it's easier actually to go this way than it was the other way. Manganese 4 sulfide means that you have, as your ion, that, right? Mn4 positive, positive 4. Sulfide never changes. It's always a 2 negative, so you have that there. So switch them, right? I always said put the metal first. Just like on the periodic table, the metals are on the left. You naturally read from left to right. So put the metals first, followed by the non-metal. If you do that and you line them up like that, and you pull the switcheroo, pull them down there. When you do that, it's Mn2S4. Do you think that's the right answer? We want to reduce that. So what's our final answer going to be? MnS2. That's right. Now realize you should be able to go back and forth with this. If I gave you this, and I asked you what the name was, you'd have to think, right? You would see that it's a metal and a non-metal. It's an ionic type of compound. You've got sulfur present, and you know that manganese is a transition metal. Okay? So it's going to be some manganese in parentheses something sulfide as the answer. To determine what manganese it is, you can't just reverse the switcheroo, right? It doesn't work because the final answer you get is a result of simplifying this expression. So you can't just automatically reverse it in the other direction and assume that it's going to work, because that would give you the wrong answer. You would tell me it was manganese 2 when in fact it was manganese 4. So what you got to look at is, okay, there's 2 sulfides present. That constitutes a 4 negative charge. That means this has to be a 4 positive. So it's manganese 4. Realize that this, I hesitate in teaching this because I'd rather you just understand it, because sometimes students apply it backwards in the other direction and things like this happen and you miss it. Okay? So just keep that in mind. Yeah, you'll always have the periodic table on the test. So if you know the alkali metals form a positive 1, you know the alkaline are... Well, that's right, but you got to use that on all your assignments, and then you'll start remembering that stuff. Okay? You'll always have a periodic table. Yeah, I'm never going to have you memorize that. That's crazy. No. Well, there's only, 5? Something like that. I mean, it's table sugar, table salt, ammonia, water. You can do that. All right. Let's write this. Iron 3 phosphate. What is the first thing I'll have to do is figure out what my symbols are involved. Iron 3 means what? Iron with a 3 positive charge. So there we go. What's the other side? Phosphate. P? P by itself would be called what? Well, okay. P, the anion with only a P would be called what? If it was P3 negative, what would that be? Is that right? Yeah, 3 negative. P3 negative would be what? Yes, phosphide. Okay? P3 negative would be phosphide. What is phosphate? PO4 3 negative. That's right. It was a polyatomic ion. Okay? So you would write it as PO4 3 negative. Put them next to each other. Switch them down. You get Fe3PO4. Remember, you got to keep these. Remember. That meant remember in my hick terms. Remember that we got to keep these separate. We can't just write a 3 after this. It's PO43 then. Okay? Keep this in a group, separated by itself. Fe3, PO4, 3. Okay? Is that our final answer? No, it's not. That is. Okay? Now you should, again, be able to work backward from that if I ask you. What do you mean? You don't have to do the switch? No, you don't. You don't have to. No, I'm not saying you have to do it this way. You're going to see that, especially in situations like this, that's easy to do. But when you have like 4s and 7s and that kind of stuff, where it's not as easy to do in your head, that will become more useful. This switching. Yeah. I would prefer that if you can do it without doing that, that's even better, because then you actually can understand what's going on here and see how they match up. Some people just. Some people have a problem with it, so I don't know. All right. Check and make sure everything balances out, and it does. So there we go. Uh-oh. Ammonium carbonate. Anything different about this one? Huh? That's right. I got 2 polyatomic ions. How do you think I write this? No trick to it. Huh? Carefully. You tread with caution. No, it's actually even simpler. Okay? I write down ammonium. There's not a lot to think about. There's just a formula for ammonium. You memorize it. It's NH4 positive. Write it down. Carbonate. There it is. CO3, 2 negative. Question becomes now, I got to put these things together to make ammonium carbonate. Well, how many ammoniums am I going to need? 2. You can do that in your head, or you can set it up like we have been setting it up. Either way. If you do that, realize you get NH4, 2, CO3. You can't reduce that anymore. Okay, so that would be the formula for ammonium carbonate. You could check it out, make sure. You got total of 2 positive here. Each one of those is a 1 positive. That's a so you've got a total of 2 positive. That's a 2 negative. That balances out, so everything's good. Okay. Now later on, I'm going to show you why these negatives and these positives occur. You know, why does a positive form? Why does a negative form? It'll blow your mind. Okay, what are the formulas for the compounds made from these ions? Copper 2 and a nitride. See if you're right. I'll write on here again. Copper 2 means what? Was that what it means? What does it mean? It means this, right? Okay. Nitride means what? Okay, so put these together. There you go. Okay, that would be copper 2 nitride. Iron 3 with a bromide ion. What's iron 3? Okay, bromide. -1. So I would write that. Iron 3 bromide. Good. Aluminum. Okay, 3 positive. Sulfate. Good. Put them together. Yep. Got it? Piece of cake? Quiz now? There was some that I mentioned that were, there was 3 of them, right, that I mentioned that were a 3 positive charge. What were those 3 on the periodic table? Aluminum, gallium, and indium, right? Is that, yeah. So those were 3 positive. Remember that zinc and cadmium are always a 2 positive. Silver was a 1 positive. You just have to keep those as exceptions from the patterns. Okay. So there we go. We were right. Nitride. So 0, 1 negative, 2 negative, 3 negative. Yeah. The N and the P you can form a 3 negative charge. The ones below that don't really, but that's okay. Because those are the only nonmetals over there. Uh-oh. I like that. It makes people scared when you say it. Uh-oh. So, you know, think about if you have kids and you hear this. You're like, uh-oh. No, it's never good. All right. Hydrosulfuric acid. How do we work backwards? Okay, well, okay, that's exactly right. You got to start somewhere. We know that it's going to have an H in it, right? So that's easy. You're right. Now, write the symbol for the anion and its charge. Now, what you've got to think backwards through is the rules for naming acids. The fact that it's hydro in front of it means what? Right, it's a binary acid. It's not a polyatomic ion. So there's only 2 elements that are going to be present. So that gives it away, right? If there's only 2 actual elements that are present, what's that other element? Sulfur. So you know your anion now. It's going to be a S2 negative. So now, how are you going to write this? You can do this without even thinking about these steps now. Good. H2S. You'll sometimes see this. It's technically an acid. It's hydrosulfuric acid, not sulfuric. Hydrosulfuric acid and sulfuric acid are 2 entirely different things. Okay? And the only difference between them is that prefix in terms of naming. Chemically, there's some differences. Oxygen is present in one, not the other. This is actually also can be called hydrogen sulfide. It's a gas. Usually it exists as a gas. It can be called hydrogen sulfide, but more, it's technically called hydrosulfuric acid. Huh? Well, I'm mentioning this because this is that smell, that sulfur smell a lot of times that you smell, rotting meat, nasty stuff, rotten eggs. This is actually this acid that is forming, sulfur that is holding these proteins together inside these cells of this tissue. The proteins start to decompose, and it releases sulfur. Sulfur is what holds the proteins together. And it starts reacting with hydrogen in the tissue, and it forms this gas, and it comes up, and it stinks, and it smells really bad. So when you smell sulfur, you technically aren't smelling sulfur atoms. You're smelling this compound that contains sulfur. All right. Everything balances out. We're good to go. Carbonic acid. Come on, get excited. Get excited about it. You're like, carbonic? Yes, carbonic acid. All right. You like carbonic acid. Some of you do. I'm looking at some carbonic acid back there. Some carbonic acid over there. Carbonic acid will pretty much be anywhere there is water and carbon dioxide present together, okay, such as in a pressurized system of a soda pop. Carbonic acid means, there's got to be an H. Otherwise, it's not an acid. Oh, there's an H first still. It's an acid. There's always going to be an H. But that's right. Since there's not a hydro on the front, it's not binary. It's not just two things. It's going to bring in a polyatomic ion with it. So then you think carbonic, okay? Carbonate, because ick and ate go together, and ite and us go together, okay? So carbonic means carbonate. There's no carbonite that I had you memorize anyway, so it's not an issue. But the fact that it is carbonate means here it's going to be carbonic, so carbonic is the way you would say it. CO3, 2 negative. Put them together, how would you write that? H2CO3, okay? Anybody studies biology at all in here, your anatomy and physiology, if you've taken it, you've had to learn about the buffer system, the carbonic acid buffer system. Even if you didn't go in detail, it was mentioned in the respiratory system. If it hasn't, it will be when you learn about respiration. When we get into acids and bases at the very end, I'll explain a little bit more about how buffers work and the interplay with acids and that kind of thing. Right now, we're just naming. So, all right, you got it. Piece of cake. So what is chlorous acid? Ci. Chlorous. First of all, is this a binary acid? No. I do have hydrogen at the front, okay? But I have a polyatomic ion. So us means ite. So what's chlorite? Good. ClO2 negative. So that would be what? Right? That would be my formula. Phosphoric acid. Now we've got no hydro in the front, right? So I still have a hydrogen there, but that just means it's not binary. That means I've got a polyatomic ion group. Phosphoric means it came from what polyatomic ion? Phosphate, which is, okay, so give me the formula. Good. Hydrobromic acid. Now we do have a hydro. That means there's only two things present. That's right. So I've got H. Bromic comes from Br. HBr. There's only one negative there with that bromine, right? That bromide ion. There you go. Oh, it's good stuff. It's good stuff. Questions before I keep going? If you're at the end of the rope, just tie a knot and hang on. We got to keep on keeping on here. Keep on going. No Joe Dirt fans? It's all right. Slap an E on it. Now it's a deer tag. All right. I'm wrapping up with names unless you have any questions. Key to this, practice. Practice, practice, practice. Get in there. just so it comes second nature to you. Because I promise you, and I'm not just trying to scare you, I promise you, after this chapter, naming is implied with what we are doing. So you're going to have to know how to name in order to complete the problems. I'm not going to say, what is the name of this? I'm just going to say, you got this, and you got to figure out the formula for it before you can do any math with it. So take the time, do all the extra problems in the back, whatever I have. Don't just focus on the homework that I have. I give you extra problems. I post all the answers to those. I show you how to get those answers. Especially with naming, something that's just over and over and over. You need to get in there and you need to make sure you know how to do that. Okay? That'll help you throughout the rest of this semester. Okay. Now, another thing. This is a little easier now. We've sort of already discussed this indirectly. I want to talk about what's called the formula mass. In other words, how much does a molecule weigh? It's very simple to calculate. What do you think you have to do? Yeah, add up the masses of all the atoms that are present. It's that simple. Okay? Now, of course, AMU, if you're dealing with an individual molecule, and I say you have Na2S, you would have to take 23 plus 23 plus, 32 for sulfur. You would have to add those together. Easy enough. This is also called molecular mass or molecular weight. So you might see these three things, they mean the same thing. Okay? Now, well, I'll just leave it at that. So the mass, for example, of one molecule of H2O, of water, would be 2 times whatever the mass of hydrogen would be, right? Plus whatever the mass of one oxygen would be. So there's just a 1 out there. If it was H2O2, that would be hydrogen peroxide, and you would have plus 2 times 16 out there. Okay, so just add up all the parts. That's all it's saying. So in the case of water, one molecule weighs 18.02 AMU, and you can see that the bulk of that weight comes from oxygen. Hydrogen is present. There's actually twice as many hydrogens present, but percentage-wise, by mass, it represents a very small portion of the water molecule. By mass, the biggest hunk is made of that one oxygen atom.